Welcome to Lecture Zero of ECE 1786, Creative Applications of Natural Language Processing. My name is Jonathan Rose. I'm the instructor in the course, and the purpose of this Lecture Zero is really twofold. One is to give you a sense of what the course is about, so you understand if you want to take it, but also to give you a really good sense of the needed prerequisites for the course, and I'll be describing those later on. They should allow you to figure out if the course is for you. It is our tradition at U of T to begin courses with a land acknowledgement. Toronto is a city of immigrants, and my parents arrived here in 1952, and it's likely that you or your parents are new to this country. That's not a new feature of Toronto. For over 15,000 years, Toronto has been a gathering site for humans, including the Wendat and Petun First Nations, the Seneca, and most recently the Mississaugas of the Credit First Nation. Today, Toronto is still a meeting place for Indigenous people and immigrants, both new and old, and from across the world. I want to acknowledge our duty of stewardship toward this land, and I'm grateful to have the opportunity to work on it. Welcome also to ECE 1786. Large language models have led the way in the tumult that is modern AI. It's enabled incredible change in how we do everything, from our work to our learning, our teaching, and our earning. The purpose of this course is really twofold in touching that world that is changing so rapidly. The first purpose is to learn how large language models are created and how they work inside, to have some deeper understanding of what for most people is a very not well understood black box. The second purpose of the course is to learn how to use a large language model in an agentic system in a large, unique project. And it's really two things in once. And in fact, it's a bit of a struggle to bring these things together. And this year I'm going to change it a little bit, as I'll tell you later on. I personally look forward to a time, maybe much sooner than we all thought, where the doctor that I go to see when I have medical issues is a computer and is really good, maybe better than a regular doctor, because a human doctor, because it knows more and is, I would suspect, could be set to be unbiased. Maybe. I also hope that people would be able to get high quality mental health talk therapy anytime, anywhere on a computer. And if that was possible, it would permit far more accessible mental health therapy and perhaps address some of the world's many ills, actually. That is part of my research in this field. I really have two major thrusts in research, which actually map to the two thrusts of this course. So let me tell you what they are. My first active work is in talk therapy. In fact, broadly, the automation of mental health talk therapy. But it's a little more focused than that. It's too big a thing to tackle all at once. So it's focused on addiction, which is a subclass of mental health. And it's even focused more narrowly on smoking cessation, helping people quit smoking. And we are trying to apply a very specific type of therapy called motivational interviewing. I won't go into what that is now. But the goal of building the chatbot, the automation, using large language models, is to take someone who smokes and move them towards the decision to quit smoking, because most smokers actually don't think about quitting smoking. And so the key first step is to get them to decide to quit. And we've been doing careful scientific measurement of the impact of the chatbots that do this on humans. And our goal is to try to control large language models to apply this therapy called motivational interviewing. Our hope is that in this somewhat more narrow context, it will read or be relevant to the automation of all talk therapy. And that's our hope. Here's a little picture of something that we did last year. We have been building chatbots and having them talk to real smokers. And this is a strange looking figure. It's a plot. The x-axis here is time over the conversation. We call it volley number, where each kind of individual delineated element here is a whole turn of conversation by either the therapist or the client, as they're called. And the y-axis here is a characterization of, in the case of the pink or reddish turns, those are the turns by the client. They are the y-axis is a characterization of how much the client is using what's called change talk, saying that, oh, maybe I could think about ways of moving towards quitting smoking, something about avoiding triggers or something like that. So what's interesting about this plot is produced by a large language model, looking at the language and characterizing the scale from being kind of sticking with what's called sustained talk, or in the positive side, moving to change talk. So this red figure here is an automatically created tracking of the nature of the language that someone has spoken. It's really amazing that this is possible to do automatically. Up until recently, without LLMs, you had to do an awful lot of work to either get humans to do that or train specific models for it. This is done with an LLM. So that's just one piece. The blue stuff is about characterization of what the therapist actually said. So that's one piece of my research. The other piece of my research is in the field of understanding what is a large language model actually doing. And our thesis is that recently, with the advent of powerful LLMs, is they started understanding in a deep way high-level abstract concepts. And so in this course, as you'll see, if you look at the mechanics of an LLM, you'll see that it's just predicting the next word or token, as we'll teach. And that seems like a very simple thing. And it seems unrelated to what I believe is actually happening, which is with the large scale, large language models now operate at very high levels of abstraction, the concept level. And so we are building tools, probes, that will provide evidence for or against this notion that the LLM is actually thinking at this higher level. And once we can do that, we think we'll be able to do all kinds of other analyses, very analogous to how we might think about humans think, actually. Here's a picture of the results. This is a sentence that's being processed by one of our probes as it's going through a large language model. And, this sentence says, finally, their mother's voice beckoned them to the dining room where the dinner was served. And, I should have said, we've built a probe, and this is the output of a probe that detects the higher level concept of ambition. And so if you were to look at this sentence and think about it, you would probably agree that it does not contain anything that's ambitious in it. And the probe is agreeing. It's below, the halfway point here. And so that's why we colored it red. That's its label, and the probe is agreeing. Look at this sentence. Emily shared her burgeoning dream with Sophie, expressing a desire to pursue writing more seriously while also cherishing moments like these. So if you look at these words, you could believe that this person they're speaking about Emily, and she's expressing ambition. And the model, the probe, looking inside the model, let's be clear what's going on here. We're looking at the representation inside the model, is detecting that, whereas this final sentence doesn't have that. So that's sort of a piece of what my research is up to. And as you can see, it's kind of mapped to the two pieces of this course, what's going on inside and using large language models. Let me speak a moment about the learning outcomes I'm looking for you to learn in this course. First of all, I'd like you to understand what a word embedding is. It is the core representation inside a transformer-based large language model. And I'm going to talk about how that gets used inside of more ordinary classification tasks before moving on to the architecture of a transformer style, which is a neural net, architecture for large language models. Its global structure, how you train it, this key idea of attention inside, the stacking of blocks of these transformer blocks, what it means, how you go from producing one token, one word, to producing many in this process called autoregressive generation, how you take something that's raw, that's trained that way, and make it behave and not do bad things. That's called instruction training. A key inner separate concept called chain of thought, which is a lot like us. And it leads to the idea of these models reasoning, which is how we talk about them these days. This is all done in the context of software or assignments in which you use PyTorch and pull some models from Hugging Face. The second major learning outcome is to understand what we'll call agentic systems. This begins with methods for prompt engineering, telling the LLM what you want it to do, and then breaking problems into pieces in what I'll call agentic decomposition, making use of techniques called retrieval augmented generation. It's RAG is its short form, using various methods to communicate between agents, such as model context protocol, various assistive systems for constructing those agentic systems, and then understanding some deeper things that are now just becoming well understood. Well, I don't think anything's well understood. Just being kind of discovered, which is the notion of curating the context that you feed into a large language model at any given step of its processing. All of this is kind of glued together with this new term, which is called a harness. We build harnesses around large language models. And in order to run them on somebody else's machine, we call an API to use them. If we can't afford that, or we don't want to go to some external system, then we'll talk about how to run a local model on your own computer. Agentic systems are really programming in a new way. It's the old kind of programming where you build procedural things, but some of those procedures may be calls to a large language model, feeding it a curated context and getting it to do a step or many steps in a process. This is the programming of the future, and it is new, complex, and there's a lot to say about how to do it right, and a lot to learn by working on a project in this space. The final learning outcome is actually engineering, and many of you have some engineering experience. My experience in this course is many of you don't have a lot. And what is engineering? In my view, that is the navigation of an open-ended problem. You start with a problem and you try to solve it by building something in a project. That's the engineering design process, where you figure out what the problem or challenge is, start to evolve ways to solve the challenge or problem, plan some, build some, and iterate to improve on it. But these first notions are of what you're going to build. I'm going to ask you to come up with something of your own to build, and we're going to iterate with you on the formation of that. And that's a key beginning engineering step. And eventually, when you communicate it in a final presentation in the course, you'll get some practice in describing what you've done, which I think is all part of engineering. This begins with crystallizing some ideas. You're going to have to articulate your ideas to your project partner. I think there's only going to be one. And then you're going to discuss it with myself and the TAs. You're going to write a proposal. You're going to present the proposal. You're going to write a progress report, do a final presentation, and then a final report. So lots of that is intense but powerful. Very quickly, there's a couple other courses that touch on the same area but are quite different. One of them is, let me just see what I was going to say here. Yeah, one of them is the CSC 2501, the graduate course. It's cross-listed with the 485 undergraduate course in computer science. It's called Computational Linguistics. It is much broader than this course. That talks about many aspects of language, its grammar and semantics in what was the original nature of natural language processing. That's completely different when you turn it over to neural networks. There's a similar course called Natural Language Computing, which is also broader on the machine learning front. So to be clear, ECE 1786 is very specific. It's going to start with word embeddings and say, here's what a transformer is and how it works and how it's trained and how it's guided. And then let's think about how to use it. These courses are much, much broader around natural language processing. The course prerequisites. Well, I said there are prerequisites. They're stated in the description of the course, but we don't actually check them here at U of T. So really, this is up to you to make your own decision. But this lecture is going to give you advice about whether you're going to run into trouble quickly or not. And as I say, most people really learn if they're going to want to stay in this course after finishing all of assignment 1. There's 4 parts to it. It's a big assignment. To be clear, this course does not introduce anything to do with machine learning. It's assumed that you have a bunch of machine learning background and depth in the theory and practice and software of neural networks. And you'll need that just to do the courses. The courses that I know here that undergrads take at U of T are this set here. This is in engineering science. These are in engineering, electrical and computer engineering. These are computer science. Any of these courses are pretty decent background for this course. These graduate courses are kind of similar to those undergraduate courses, and they're also acceptable. ECE 1513 is machine learning, 1508 applied deep learning, and MIE 1517 is like applied deep learning. I have seen that APS 1070, Foundations of Data Analytics and Machine Learning, is not really a good background. It isn't technical enough. If your undergraduate degree is from elsewhere, and that's many of you, you should have taken a course that's equivalent to one of those at U of T. And I'm going to describe that detail, though what's in those courses in a little more detail, so you can kind of figure that out. So you need to know machine learning. What's that? Well, it's about classification sometimes, or regression, which is similar to saying, well, what's logistic regression or linear regression if you're going to use a linear classifier or regressor. There's the question of binary versus multi-class classification. Should be clear to you. Supervised versus unsupervised learning. Data labeling, what that means. In the neural network space, you need to know what a linear neuron is, its weights and biases, what a nonlinear activation function is, and examples of it like sigmoid or ReLU, what a multi-layer perceptron is, what a loss function is. For example, binary cross-entropy or multinomial cross-entropy, what the softmax function is, what training, validation, and test sets are, why you need all of those. And actually, very interestingly, that shows up in a new form in this course. What a training and validation curve is. Actually, it shows up in the old form and the new form. That's to be fair. Gradient descent to optimize a neural network to be good at doing the thing you want it to do. Stochastic gradient descent, key concept and all of that made this stuff work. Hyperparameter tuning, because we got to try and figure out what the black box needs. That includes regularization, things like normalization, dropout, and weight decay. In more advanced neural networks, I'd want you to know for sure, because we'll be using this, what a convolutional neural network is, its kernels, batch normalization. Perhaps it's good to know about recurrent neural networks. They've really gone out of fashion, maybe coming back a little bit into fashion for various reasons. You should know what transfer learning is. It's the thing that makes everything work in these worlds of a pre-trained network and the fine-tuning of it. You need to know how to build all that with software frameworks, like having experience in TensorFlow or PyTorch. PyTorch seems to be dominating these days. You should have written full training and test loops for applications with significant data size. You understand what tensors are, what their shape is, how the NumPy framework helps you work with that, and a really subtle thing, which is how to debug a neural network. It's very different than debugging regular software, and so expect you to have some experience in that, along with the data science concepts that are kind of essential to making lots of things work. What's a false positive, a false negative, true positive, true negative? What is sensitivity and specificity? Why do we measure the goodness of a neural network with the area under the ROC curve? And what is a confusion matrix to study whether things are working or not? Okay, so that's the background you need. That, and together with assignment 1, you'll be able to figure out if you will be able to succeed in this course. Let me spend a moment telling you my teaching philosophy, which is sort of showing up already in what I've described, but let's be explicit. In this course and in many, I prefer to teach less, teach fewer things, but teach them more in depth. And I want to be able to explain the intuition behind the approaches of what I'm talking about so that there's some kind of human intuition, because I'm not so fond of, which is very common in this field, talking about pointing at equations and getting people to just understand something by looking at equations. I believe, so I'm sacrificing depth for breadth. No, breadth for depth. I'm sacrificing breadth. I'm not covering as many things, but I believe if you get good intuitions, you can go off and learn things on your own more quickly. I also believe that learning comes from doing, writing your own software and experimenting with it, and answering questions about what happened and thinking about it and reflecting on it. And finally, I deeply believe that we engineers need to learn engineering in whatever subfield we're working in by doing open-ended projects. I think it's so powerful to learn to conceive a project, to have an idea and bring it to reality. And on the way, you have to kind of have the idea, understand what it is, but also why it's important to do it or solve it. And then only then to figure out how to solve it, which we tend to jump to quickly as engineers. And then if you can describe it, then maybe you would have learned something. So all of those things are key in open-ended projects. Okay, let me give you some details about the course. New this year, I think I mentioned briefly, but I want to say it again. There were these two parts of the course. How does an LLM work inside? And then let's build something with it. And it was two separate sections of the course. The 60% project is based on the second part, and there you have to cook up an idea and then execute it. And because I would talk about that late, it made it harder to jump into the project. So what I'm going to do is interleave the internals work and assignments with the agentic stuff. So that has a bad side effect because it kind of means I'm going to be changing the topic a little twice. I'm going to jump into this and jump out and jump into it again. So it's an imperfect sequence for the logical flow of the course, but it's better for the project. And I think the project is the key thing you'll take away from this course. Well, and a good intuitive understanding of LLMs as well. So the grading of the course, 40% of the grade is for software assignments. 60% of the course is the project, broken out into a lot of different pieces: a proposal, both document and presentation, a progress report, a final presentation, a final report, and the software you create, and then something called the peer review I'll describe in a moment. I think this is when all the assignments are going to happen. There's a change in the order from previous years where we're talking about agentic methods in the second assignment. There's a free textbook online from Jurasky and Martin. I've got the link to it here. You can pull it off the slides. It keeps getting updated every year. They did a major change this year. I really like it. They've oriented it more the way I like teaching this course, actually. They morphed an old kind of speech and language processing book into a new kind, and they think they finally got it right this time. They've never written in this new edition a first chapter, but there's an old version of the first chapter, which will suffice, that I've linked here. A quick note on the computers you might need in this course. In any deep learning neural network kind of context, there's always a question, do I have enough computing power to do this stuff? My suggestion now, I think it's settled down, you can use Google Colab. If you're willing to spend $14 a month, you can get Colab Pro, and that will give you sufficient computing power for most things in this course, particularly the assignments. Pro Plus gets you even more. Let's talk about that project. It's going to be done in groups of 2, and so very soon into the course you should find yourself a compatible partner, and make sure you're honest about what your capabilities and background are, and make sure you're honest about what your availability and how much effort you're going to put into this. Finding a compatible person is a really crucial thing to do here. The topic will be of your own choosing, but it must be approved by me, the instructor, and we will help you evolve that topic. But the ideas, with some stimulus from me, will come from you. They must use large language models, and possibly multimodal models, ones that do have more than just language coming in and out, but perhaps sound or images or even video. But so you must use those in an application. What application? Well, that's where the big question is. Here I'm only saying you should use them in what we're now calling an agentic system, which is often we can't do it with a single model. If you can do it with a single model, it's too simple, actually. So you'll have to make it harder. I like this new term where we say we've got a large language model, maybe lots of them, and we build a harness around them to get them to do what we want them to do. They don't always do what we want them to do. And so there's a lot to think about how to make each individual step work, which is different from regular programming. If you get my permission, it is possible to break out of this rule and say, oh, I just want to do old school training. But that has to be a long conversation with me and needs to be some kind of research project. In my view, the future is learning to program these hybrid systems, regular software collaborating with large language models, which they themselves may call regular software. It's a complex world. Learning that's the programming of the future. So pretty much I'm pushing people towards only that methodology because it's new and we need to all learn how to do this. So the project has to be an application, again, like an agentic system. Often one of the things you're going to need to do there is validate that any given step produced by any inference call to an LLM, you're going to have to be sure that that's going to work because it might not, as you'll learn from the other part of the course. So I'll be trying to teach that. Here's an amusing elephant in the room for this particular course. It's a course about AI and large language models, which turn out to be really good at writing code. In particular, I've been amazed at what Codex, Claude Code, I haven't used Gemini, but I hear it's just as good, is capable of doing. They're incredibly powerful. They're also incredibly powerful at destroying your ability to learn. So the deep question for a learner is, how much should I use these things to do my work for me? That's the big problem of all education. So let me be clear about what you are and are not allowed to use in this course that's actually about the thing that's causing this problem. For assignments, I'm going to restrict your use of AI coding. I want you to understand the software that you need to build in the assignments. You can use a coding agent to explain how to code something in a rough sense, but you must write the code yourself. And you must report to me and sign that you're honestly reporting how much AI you've used in the assignment and give some detail, some examples. I'm gonna hold you to that because you need to be held to that. Otherwise, you won't really learn what's going on inside. You'll something will just take you there. On the other hand, for the project, you can use AI coding extensively. It is remarkably powerful. You can't just say, go do my project for me and come back later. You have to work with it. It has to be your partner. And you have to do some thinking and some structuring and some motivation, some proper motivation and decomposition, let's call it. It should be your partner, not the boss. And one of my colleagues captured this well. Professor Chen Ying says, think first, use AI second. I will be expecting impressive projects as a result. We can do amazing things in our work and our research. We can build these viewers without much work that just show what's going on in a way that was never possible before. So I'm excited to see what great things you can build. And you're kind of unleashed in the project, but not in the assignments. Here's the tentative restructured, because I've reorganized the course, timeline of the project. You should have a group of 2 by September 22nd. You'll be required to get my approval in principle. I'll show you a form that says this has got to give a rough statement of what you're thinking, and that's due on October 13th. A written plan and a presentation is due on October 26th, and you'll present those in one of 3 sessions on the lecture or in the evening of the lecture or the next evening. You'll present that in person. Progress report is due on the 17th. The final presentation is in also one of 3 in-person presentations in the week of December 8th. Excuse me. And a final report will be due on December 15th. You are now warned. Do not book a flight before this stuff is due, especially you got to be here during a presentation. Do not book a flight. Not finally, one of the other things you're going to do is give other groups feedback. I'm going to ask you to give feedback on their proposal presentation and document and on their final presentation so that they can improve their final report. So, and we'll grade that, your feedback for quality. Let me tell you a little bit about myself and the TAs. First of all, I've been a professor here for a long time, since 1989 in electrical and computer engineering. And as I said, my research is on both the automation of talk therapy and exploring concept level understanding of LLMs. But strangely, my previous field of research was quite different. It was all about the architecture and software needed in the design and creation of field programmable gate arrays, FPGAs. I have some experience in entrepreneurship, started a company in this field with some grad students. Company was acquired by another company, and I was a director of software engineering there for 3 years. That company was called Altera. It was acquired by Intel, which recently spun it back out as Altera. I also ran the department for 5.5 years, from 2004 to 2009. I still oversee, for a little bit longer, the entrepreneurship hatchery here in engineering, and have lots of letters past my name. Now, special note for this year only. This is, I'm making this video on August 9th, kind of early, because this week I'm going to undergo a surgical procedure. I need a new hip. And this may keep me from attending the first 1 or 2 less lectures in person. If that's the case, then I will broadcast in real, synchronously, as we used to call it, those 2 lectures online. If that's the case, I'll send out an announcement prior to the first class that says, okay, we won't go to the class, we'll do it online. If I do that, here's what I'm going to be asking you to make it more closer to in person. I'm going to ask you to all turn on your cameras. I know having your camera on means you have to wake up and be there. That's what you have to do in a class. So I think it's okay to ask people to turn their cameras on. So don't be surprised that I won't start the lecture until you all turn on your cameras. I have 4 teaching assistants. Jiding Zhu is one of my PhD students who's taught this course with me several times. A wonderful mentor in the projects. He works on the talk therapy chatbot. Solomon Ali is another one of my PhD students, and he's working on the concepts in language models project. So you're seeing both sides of my research there. Mohammad Reza Safavi is not my student, but he works on architectural efficiencies of LLMs, and he's just finishing his master's degree. And Cindy Wang is a master's student of mine working on the talk therapy work as well. All of these people have taken this course. There will be 3 course websites. The regular Quarkus site where you'll get your assignments and grades and get announcements. There's a Piazza side that's now up and running. I just turned it on today. You can access it via Quarkus. And there's a public website that replicates most of the content that's on Quarkus. So that's up and running right now, and you can get at that too. So if you have any questions, you can post them to the Piazza site or bring them to the first lecture. If it's in person, it'll be in the room GB 248 on September 8th at 9 a.m. Or online, depending on how I'm doing after surgery. So I look forward to seeing you then and joining me on a great journey towards learning one of the more important things that have come along in a while.